Hello and welcome back to Math 104. We are going to pick up right where we left off, which was simplifying radicals, specifically square roots. Understanding how to simplify radicands that are constants versus variables, and of course a combination of the both underneath the square root sign. One of the things that we focused on was separating each base that was under the square root sign, so essentially each base that was part of the radicand, and then we would identify the perfect square factors for each of those bases. So we're going to continue with that idea and then perform operations on radicals. So let's see what we can accomplish in today's session. All right, let's check it out. We left off with part I, which was the square root of 45, x to the 6th, y to the 5th. The very first thing we learned was it may be helpful to us to essentially split each of my bases up under the radical. So we have the square root of 45, the square root of x to the 6th, and the square root of y to the 5th. Right away, I noticed that my square root of x to the 6th happens to be a perfect square factor. So I can evaluate that no problem. But I do want to break each of the other two radicals down as well. So with square root of 45, my perfect square factor is 9. So we see that 9 times 5 gives us square root of 45. The square root of x to the 6th, remember power over root, your root is 2, so it's like saying 6 divided by 2, which is 3. So we apply the square root and we get x to the 3rd power. Now with square root of y to the 5th, we recognize that we could evaluate square root of y to the 4th, but not y to the 5th. So what we want to do is break it down. So we have y to the 4th times y to the 1st. Again, keeping in mind the product rule. I'm going to highlight each of my perfect square factors. So 9 is a perfect square, and y to the 4th is a perfect square. So now let's evaluate. The square root of 9 is 3. We're left with the square root of 5. I have x to the 3rd, which it literally stays exactly as is because we finished applying the square root to x to the 6th. So I'm just simply bringing that down. Square root of y to the 4th is y to the 2nd power. And of course, we still have square root of y to the 1st. As we learned in our previous problem, we're going to essentially collect all of the bases that are not underneath the square root, and we'll write that first. So we'll write down 3 x to the 3rd, y to the 2nd, and then we're going to collect all of the bases that are underneath the square root, which happens to be 5 and y, and we'll combine those like so. So our final answer is 3x to the 3rd, y to the 2nd, square root of 5y. Keep in mind that everything is connected by multiplication. It's 3 times x to the 3rd times y to the 2nd times the square root of 5 times y, right? Just something to think about as you evaluate these radicals. Take a look at part J. We're going to break this down again. So square root of 25, square root of x to the 5th, and square root of y to the 8th. The really cool thing about this one is that we have 2 perfect squares already. So I'm going to highlight those. The square root of 25 is simply 5. Now square root of x to the 5th, we're going to break down as x to the 4th times x to the 1st. And then square root of y to the 8th is simply y to the 4th. Remember, you're just cutting that power in half. Now underneath that square root, we have another perfect square, and that's x to the 4th power. So let's go ahead and evaluate that. We have 5. Square root of x to the 4th is x to the 2nd power, but we still have square root of x, so we're going to leave that. And then we have y to the 4th. Let's collect all of the bases that are not underneath the radical, and we'll put them together. So 5x squared y to the 4th, and then of course we have square root of x right after. And that concludes that particular problem. I'm hopeful that at home you had an opportunity to try these on your own prior to seeing these during this live stream. And otherwise, if you happen to work on this in the previous video, and then you can verify during this video as well. But the point is, I hope you tried this on your own first. That's going to be really, really helpful. Now remember, we're looking for perfect square factors. I don't have any as is, so I do have to break down each one of these. Notice with square root of 40, our perfect square is 4. Some of you may think, oh, that breaks down into 8 times 5. True, neither of those are perfect squares. So be careful as you break this down. So 40 will break down into 4 times 10, where 4 is my perfect square factor. This is what I'm looking for. This is why I like using the highlighter, because it forces me to look for that perfect square. X to the 11th breaks down into x to the 10th times x to the first, I can't even talk. And then square root of y to the 15th breaks down into y to the 14th times y to the first. Cool. Let's highlight each of our perfect square factors. Beautiful. And now let's evaluate. Square root of 4 is 2, but we still have square root of 10. Square root of x to the 10th, cut that power in half. So it's x to the 5th, but we still have x square root of x. Square root of y to the 14th, cut that power in half. It's y to the 7th, but we still have square root of y. Let's collect all the bases that are not underneath the radical. Let's put them together. And then let's collect all of the radicands and put them together under the same radical sign. So you have 2x to the 5th, y to the 7th, square root of 10xy. And that concludes this page. Beautiful. I hope that your work agrees with mine and that you were able to kind of work through this step by step just like I did, and you identified each of your perfect square factors. Very cool. Now, what happens when you have fractions that have square roots, right? Notice at the very top, I wrote here that the square root of a over the square root of b, so a fraction of square roots is the same as the square root of a fraction, okay? And vice versa. So sometimes it's helpful to look at a fraction of square roots as a single fraction where you can reduce if possible, but sometimes it doesn't help either. So it really just depends on the approach. So it depends on the information that we're provided. And I'll show you exactly what I mean by that. So let's start with part A. We have square root of 36 over 4. Immediately, I want you to recognize that 36 divided by 4 is simply 9. So the first thing we do is we divide what's underneath the radical. That leaves us with square root of 9, and we could say, oh yeah, that's no big deal. That's just 3. You could have taken the square root of each of these. So the square root of 36 is 6. The square root of 4 is 2. 6 divided by 2 is 3. You would have had the exact same answer. I believe that it is helpful to simplify first whenever possible. Part B shows you immediately why that is. So notice that we're not going to be able to take the square root of 2, and we're not going to be able to take the square root of 50, right? So instead, what we want to do is simplify the fraction. We want to reduce. So I say to myself, if I had 2y to the first, z to the third, all over 50 z to the first, immediately I would say, well, 2 goes into 50 25 times, and then z goes into z to the third twice. So now let's rewrite this. Keep in mind we have a square root. So we have the square root of, in my numerator, I have y to the first, z to the second, all over 25. What we'll want to do at this point is we'll want to kind of do the exact same thing we did on our previous page, which was to separate each of our bases just so that we could see what was going on. Now, as you become more proficient, this is probably something you're not going to do too much of, but because we're beginners and we're just starting to understand how to simplify radicals, I want you to progress in this fashion until you start to see the pattern and you start to recognize the little shortcuts that you can take. As always, I'm going to highlight my perfect squares. So it's a reminder to me that I can take the square root of each of those. So square root of z squared is simply z. And notice in my numerator, I still have a square root of y. And then in my denominator, square root of 25 is simply 5. And that actually concludes the problem. So simplify your fraction first, then separate each of the bases underneath the square root, and then of course simplify further by evaluating the square roots. Okay, let's do it again. So instead of rewriting the problem, I'm just going to simplify and show you what's left. So being very careful, I see that 3 goes into 15 5 times. Okay, so that takes care of that. I have x to the first in my numerator and an x to the 9th in my denominator. According to the quotient rule, I'm going to keep the base, subtract the power, and leave it where it's heaviest. So 9 minus 1 is 8, which means I have 8 x's in my denominator. Notice here I have a y to the third in my numerator, y to the first in the denominator. 3 minus 1 is 2, and it's going to be left in the numerator. And then last but not least, I still have a z to the fourth in the numerator. So the first thing I did was I simplified underneath the radical. I simplified that fraction by reducing, by dividing out common factors. Now I want to rewrite this, so it's a square root of 5, the square root of y squared, the square root of z to the fourth, all over the square root of x to the 8th. Everything is separated, so now I can highlight each of my perfect squares. I have a perfect square in each of these locations. Square root of 5 is as reduced as it gets. Let's start with the perfect squares. Square root of y squared is y to the first. Square root of z to the fourth is z to the second power. But then I still have a square root of 5 in the numerator, and that's okay. It's not a big deal. Square root of x to the 8th, cut that power in half, x to the fourth, and you're done. Typically, I like to leave my variables in alphabetical order, so I would typically put y before z or x before y, that kind of thing. Perfect. Take a look at part D. Notice here we have square root of 50 divided by square root of 2. That is essentially the square root of a fraction, right? We can literally look at this as the square root of 50 over 2. But 50 divided by 2 is 25. So then I have the square root of 25, which is a perfect square. So let's actually evaluate that. Square root of 25 is 5, and you're done, right? No big deal. Now, what I'm trying to hint at is that even if they're split up into two separate fractions, go ahead and reduce. Reduce to make life easier. So notice that 8 can go into 72, right? Remember, we still have a square root. So I'm just going to write a square root and then draw my fraction bar and see what's left. 8 can go into 72 9 times. Notice x squared and x squared, these divide out. And then notice you have y to the 5th over y to the 7th. Quotient rule says keep the base, subtract the powers, and leave it where it's heaviest. And that'll be in the denominator. Notice each of these are perfect squares. So this time, instead of rewriting it, because remember, we're becoming more skillful, we're becoming more proficient at this, we know that I'm going to take the square root of each of these terms of the fraction. Square root of 9 is 3. Square root of y squared is y, or y to the first. And you're done. Let's do it one more time on this page. So we have 128 and 16. Let's see if a 128 is divisible by 16. It is. So I'm going to go ahead and just write a fraction under a square root. 16 can go into 128 8 times. A to the second over a to the fourth leaves us with a to the second in the denominator. B to the fourth over b to the first leaves us with b to the third in the in the numerator. It's heaviest up top, so we're going to leave b to the third in the numerator. Now, it will be helpful to me to look at this as square root of 8, square root of b to the third over square root of a squared. The only perfect square that I have in this expression is here. The other two pieces in the numerator both have to be broken down. Square root of 8 breaks down into square root of 4 times 2, where 4 is my perfect square. Square root of b to the third is b to the second times b to the first, where b squared is my perfect square factor. Okay. Square root of a to the second is simply a to the first. Now, let's note what these become, and we're going to just combine our answer and clean it up simultaneously. Square root of 4 is 2. Square root of b squared is b. And then I still have the square root of 2b. We're going to combine these under the same radical, of course, and then our denominator is a. If we had, for instance, a 2a squared root of 2b all over a, the a's would actually divide out. But because they're not the same variable, clearly it's not going to divide out in this case. And you are all set. I hope that by me, kind of jumping to let's write this simplified form in the correct order, I hope that that was okay, especially since we've seen so many examples already where I showed you each of those individual steps. Good. We are now ready to add, subtract, and multiply square roots. This section I absolutely love because essentially if you can add or subtract terms with variables, then terms with radicals is the same exact idea. So for instance, if I said to you, hey, what's 2x plus 5x? You would say 7x. 2x's, 5x's, or 7x's. Okay, cool, no big deal. If I said to you, what is negative 9y plus 4y, you would say, easy, negative 5y. Negative 9y plus 4y is negative 5y. The point here is that, didn't you just look at the coefficients and you combined them, but then you kept your variable? This is the exact same idea, where the radicals are treated like variables, right? So for instance, just to kind of throw this out there, if you had 3 square roots of 2, and I wanted to add another 5 square roots of 2, I would now have 8 square roots of 2, okay? So something to think about as we progress through this. You are already familiar with the strategy of combining like terms. You are already familiar with looking at the coefficients of variable terms to combine them and then keeping the variable exactly as is. That idea does not change when we are adding or subtracting radicals. Multiplying is a whole different ballgame, but you already know that. Addition and subtraction versus multiplication and division, those are typically always different sets of rules. So let's check this out. I think you're going to really enjoy the addition and subtraction. And then we'll just have to keep, a watchful eye when we multiply radicals. But I'll show you that in a bit. Let's take a look. Like radicals are radicals that have the same index and radicand. So for instance, square root of 5 and 4 square roots of 5. They have the same index, they're both square root, and they both have the same radicand, 5 and 5, right? So those two are like radicals. You can add or subtract like radicals, but you cannot add or subtract unlike radicals. So for instance, if I had, this is great, let's look at this side box. If I had square root of 9 plus square root of 16, is that the same as square root of 25? Well, let's check this out. We know that square root of 9 is 3. We know that square root of 16 is 4. And we know that square root of 25 is 5. Oh, it's not the same. So we're not able to just add radicals like this. This doesn't have a true meaning. This is not mathematically sound. The one above, we have 6 plus 2 square roots of 3. This is like saying, hey, is 6 plus 5x the same as 11x? And I hope you would all say, absolutely not. No way. So 6 plus 2 squared to 3 will never give you 8 squared to 3. This is not true. It would if you had 6 squared to 3 plus 2 squared to 3 is 8 squared to 3. That one will work. Yes, because those are like radicals. So it's the same exact idea with our variables when we were learning how to combine like terms. Another example, let's clean this up. 7 and 10 make 17. 5 squared to 3 minus 1 squared to 3. Remember, there's a 1 in front. If it helps, go ahead and write 1 right in front of that square root of 3. So 5 squared to 3 minus 1 squared to 3 is 4 squared to 3. And that's your final answer. You actually cannot go further than that because those are not like terms. All right, let's do it. When we add or subtract, keep in mind you probably have to simplify radicals and then you combine like terms. Okay, so we're just putting all of the things we learned about simplifying radicals together with this whole addition and subtraction piece. Cool. Let's take a look at square root of 28. Oftentimes I like writing the work on the side just so that it doesn't get super cluttered. Square root of 28, let's break that down. 4 times 7 is 28, right? Where 4 is my perfect square. See, I still have my highlighter because it's pushing me to make sure that I identify the correct perfect square. Let's look at square root of 63. With square root of 63, we notice that 9 and 7 give you 63, where 9 is our perfect square. Square root of 9 is 3. Okay, so far so good. But check this out. This reads 3 times square root of 28 plus 2 times square root of 63. Well, square root of 28 is 2 square roots of 7. Okay, hold on. So you're telling me that this square root of 28 becomes 2 square roots of 7. Interesting. So 3 times square root of 28, which is 2 square roots of 7, plus 2 times square root of 63, which is 3 square roots of 7. So let's fix this. 3 times 2 square roots of 7 is 6 square roots of 7. You only multiply the coefficients. Coefficient times coefficient. 2 times 3 square roots of 7 is another 6 square roots of 7. And then let's combine like radicals. It's like saying, what's 6m plus 6m? You would say, well, 12m, right? But in this case, that m is square root of 7. So this gives us 12 square roots of 7, and you're done. Not bad, right? Make sure you break up your radicals on the side. That way it doesn't get super, super cluttered. Let's look at B. Square root of 27, let's break that down. 9 times 3 will work because 9 is our perfect square. So this gives us 3 square roots of 3. That's going to replace the square root of 27. So I have 2 times 3 square roots of 3 plus 5. Now let's take care of square root of 8. Wow, square root of 48. I can talk. We've evaluated square root of 48 already on our previous pages in this unit. We know that 16 goes into 48. So some of these common ones, it's going to be really helpful for you to like commit to memory what those largest factors are, largest perfect square factors. So this is going to be 16 times 3. 16 is our perfect square. So that gives us 4 square roots of 3. Let's go ahead and replace square root of 48 with 4 square roots of 3. And then minus 4, but we have square root of 12. So let's break that down as well. 12 can break down into 4 times 3, where 4 is my perfect square, and that gives us 2 square roots of 3. So let's go ahead and write that in the parentheses. All right, let's drop parentheses by multiplying. So we get 6 square roots of 3 plus 20 square roots of 3. Remember, you're just multiplying the coefficients. You're not allowed to take a coefficient and multiply by what's under the radical. It doesn't work that way. Minus 4 times 2 is 8 square roots of 3. Now, if we simply move from left to right, notice these are all like radicals. They all have square root of 3, square root of 3, square root of 3. Cool. So we have 6 plus 20, which is 26, minus 8, which is going to give me 18. So our final answer is 18 square roots of 3. Good. Take a look at the next problem. We have square root of x to the 4th minus square root of xy squared minus y squared of x. At this point, again, if you are watching at home at a later time, pause the video. Try out part C on your own, making sure to break down each of these terms, and then see if they're like radicals. And if you do have any like radicals, combine those. But be very careful with evaluating each term and simplifying all the way, okay? But if you are here with me, let's scope this out together. First things first, I notice with my square root of x to the 4th, this very first term, that's a perfect square. Square root of x to the 4th is just x squared. I love it, so I'm not going to do anything there. For my second term, do you see that I have a perfect square underneath that radical, and that's y squared? So we're going to go minus. Now we know the square root of y squared is simply y. But I can't forget that I still have a square root of x, so that doesn't go away. And then notice this is as simplified as it gets. There's nothing else I can do there. So I'm just going to bring down the minus y square root of x. Now recognize that I only have 2 like terms. And that's these two guys, because they both have the same radicals, right? Square root of x, square root of x. So when you think about this, I want you to imagine that this is x to the 2nd power. You don't have to imagine that. It's actually there. But what I mean by that is, what if you think of this as negative 1y squared of x minus 1y squared of x? Well, combine their coefficients. A negative 1 and another negative 1 give you a negative 2y square roots of x. It's interesting because the entire set here, this y squared of x, these variables that are associated with each other, because they're exactly identical, that's what lets us combine these coefficients. If I had, for instance, so if I had, let's say that I had negative 3y square roots of x plus 4 square roots of x. These are now not like terms. These are not like terms. Not only do they have to have the same radical, but they'd also have to have the same variable, right? Just like before. Like for instance, so I'm going to write not like terms. For instance, before when we were just looking at polynomials, if you had, negative 5xy plus 3y, these are not like terms. You would not be combining these. So that idea does not change when we introduce radicals. We want to be very careful. These would be like if they both had y square roots of x, y square roots of x, but this is missing out y, so they're not like radicals. Just like here, these would be like terms if they both had xy. This only has a y. So these are also not like terms. Keep that in mind as you move through these problems. They have to be completely identical in terms of the variables. Okay? Perfect. Let's multiply. Now, the product rule for radicals, this is pretty cool. A square root of a times square root of b is actually the same as square root of a times b. But you know that. You know that because we've seen this a million times when we broke down the radicals. We broke down the radicals using the product rule. Now notice what you have here. When you multiply, notice we have a squared to c times b squared to d. When you multiply, you can multiply the pieces that are not underneath the radical. So a times b gives you ab. And you can also multiply the pieces that are underneath the radical. So c times d. Does that make sense? Multiply the coefficients, multiply the radicands, and then put it together. And then, of course, you would simplify if possible. All right? So let's take a sneak peek. When I look at something like square root of 3 times square root of 3, I know that this answer is going to be 3. Let me explain why I know this. First off, when we think of square root of 3 times square root of 3, we know that that's the same as square root of 9, okay? And we know that the square root of 9 is 3. So let's kind of play around with this idea. Square root of 5 times square root of 5 is square root of 25, which is 5. So square root of 5 times square root of 5 is 5. Okay? So square root of 12 times square root of 12 must be 12. Square root of x times square root of x must be x. Are you getting the pattern here? Square root of m to the 5th times square root of m to the 5th is m to the 5th. So because you have the product of the same radicand right underneath the square root, it's essentially like taking that base and squaring it, then taking the square root. Well, the square root and the square cancel each other out because they're opposites. The opposite of square root is square. The opposite of square is square root, which is actually what we're going to use when we solve radical equations. So I want you to kind of keep that in mind. But you don't have to just jump to the answer like I did if that makes you uncomfortable. So for instance, with our problem here, if you wanted, you could write that square root of 3 times square root of 3 is square root of 9, and then you could say, okay, that's 3. So it's totally up to you. Let's take a look at part B. For part B, notice that I have 3 times 2, which is 6. Square root of 5 times square root of 5 is 5. But I'm going to prove that to you. Square root of 5 times square root of 5 is square root of 25. Well, there's our perfect square factor. So square root of 25 is 5, and 6 times 5 is 30, and that's your answer. If I said, well, I know 3 times 2 is 6, and then square root of 5 times square root of 5 is 5, and 6 times 5 is 30, boom, I'd be done. So we don't necessarily have to rewrite it in this form. I could literally say, well, I know 3 times 2 is 6, and I could say, I know square root of 5 times square root of 5 is 5, and then, okay, that's going to give me 30, right? So just kind of keep all of this in mind as you move through these problems. Square root of 3x plus 1 times square root of 3x plus 1. This is actually the same. So I want you to think about this being in parentheses. So if I multiplied 3x plus 1 by itself, so meaning if I take 3x plus 1 and multiply by 3x plus 1, I have 3x plus 1 squared. But this is still underneath the square root because I haven't evaluated. Notice that the square root and the square cancel each other out. So your final answer should be 3x plus 1. Okay? Keep that in mind. Square root of 3x plus 1 times square root of 3x plus 1 is simply 3x plus 1. Same thing with part D. The square root of 7x squared is simply going to be 7x. Okay? Cool. Now that we've got that down pat, let's try some that are just a little bit more complicated. It's not a big deal. We could multiply first and then simplify if you would like. Sometimes it's easier, sometimes it's not. 3 times 12 is 36. So I have the square root of 36x under the same radical because 3x times 12 is 36x. We're allowed to do this because we're multiplying. This ended up being pretty cool because 36 is a perfect square. So square root of 36 is 6, and don't forget you still have x under the square root, and so you leave it there. You're done. take a look at the next set. So let's actually multiply these first. Why not? 3 times 6, 18. X to the 5th times x to the 4th. Keep the base, add the powers. All right, let's split them up. I have square root of 18, and I have square root of x to the 9th. With square root of 18, if I wanted to break this down into a perfect square and its other factor, that's going to be 9 times 2. Let me go ahead and highlight that 9. There's my perfect square. And then with square root of x to the 9th, remember, if it was just one less, it would be a perfect square. So we essentially rewrite it as x to the 8th times x to the 1st. Square root of 9 is 3. Square root of x to the 8th is x to the 4th. And then we still have square root of 2 and a square root of x. So let's put that together. Square root of 2x, and you're done. All right. At this point, same thing. If you're watching at home, please pause the video so you can try parts C and D prior to actually checking out how I do it. You got to give yourself a shot, right? Give yourself a chance. Make sure that you're understanding this concept. I don't want this to be overly complicated for you, so follow those steps, multiply together, then break it down if that's easier, okay? I do personally have a different approach to these. But I want it to be as simple as I possibly can make it. And I think that's probably the simplest way. Okay, let's check it out. Square root of 10x to the 2nd y times square root of 5xy to the 7th. I don't know about you, but my eyes are immediately drawn to this x squared. So I'm going to highlight it. Okay. Now, call me crazy. But I know that the square root of x squared is simply x, so I'm actually just going to take it out, okay? Then I'm going to multiply everything else. So 10 times 5, 50. I still have an x. And y to the 1st and y to the 7th, that's y to the 8th, okay? So I have all these pieces together. Now I'm going to break up each of these bases. So we have x, we have a square root of 50, we have a square root of x, and we have a square root of y to the 8th. This is cool because I already have a perfect square here. Notice that square root of 50 will break down into 25 times 2, where 25 is my perfect square. Square root of x is going to stay. We can't do anything with that. And then square root of y to the 8th simply becomes y to the 4th. We cut that power in half. All right, now let me just clean this up. We see that square root of 25 is 5, so it's going to come first. I have an x, I have a y to the 4th, and then I have the square root. I still have a 2 and an x under the square root, so they go together, and voila, we're finished. Okay, for part D, we have square root of 3y to the 4th. Are your eyes drawn to that too? As soon as I see this, I think, oh, perfect square. Then we have z, and then times square root of z. Square root of 20z. Man, I can't talk. It's been a long day. Immediately, square root of y to the 4th, I'm just going to say, I know that's y squared. I'm not going to overcomplicate it. Then I have 3 times 20, which is 60. Z times z, which is z squared. I see another perfect square. And you know what? I'm just going to highlight this right now because I know that's gonna end up coming out. So I have y squared. The square root of z squared is z. But then I still have square root of 60. When I think about breaking down the square root of 60, I'm still looking for a perfect square. So when I break 60 down, I'm going to try to identify some sort of, largest perfect square factor. So I'm going to divide by, maybe we'll check 25, we'll check 16, we'll check, et cetera, et cetera. So what we'll end up finding is that the largest perfect square factor that goes into 60 evenly is 4. So we have 4 times 15 gives us 60. But 4 is a perfect square. Okay, let's write our answer. Square root of 4 is 2, so I'm going to put that first. Then I have y squared z. And then I have square root of 15. And we're done. 15 does not have any perfect square factors. That's why we would leave it as is. Beautiful. With these problems, for example 33, that concept doesn't change at all. This is simply a monomial times a monomial. So even though I had parentheses here in this example and I don't have parentheses here, the concept does not change. There's nothing special that changes because this has sets of parentheses and this one doesn't, right? It's the same idea. So 2 times 4, that's 8. Square root of 3 times square root of 5 is square root of 15. I can't break down square root of 15, so we're done. Take a look at this one. 2 times 5, well, that's 10. Now let's multiply what's under the square roots. I have a 3. X times x is x squared. And I have a y. My eyes are drawn to that x squared because that's a perfect square factor. The square root of x squared is x, so I'm going to bring that right out. And I'm left with square root of 3y. We can't simplify square root of 3y any further, so we're going to stop right there. Okay? Very cool. Very cool. Well, what happens when we have to distribute? The process doesn't change. It just looks different. That's the one thing that I really love about all of this stuff that we're doing. The process doesn't change. It just looks different because it's new content, it's new material, but really it's not new. We've seen this before. If you see a set of parentheses with a coefficient in front, you're going to distribute. You always distribute to drop parentheses. That's never going to change, and it's not going to change here. So the only difference is we just have to simplify. We distribute, then we clean it up, right? Always, always, always. This is just a little bit different because it's radicals, but it's the same process. It's the same concept. Let's check it out. I'm going to distribute. So we have 3 times 75. That's going to give me the square root of 225. Remember, I'm allowed to do this because they're both square roots. Plus, and then we have the square root of 3 times the square root of 27, which is the square root of 81. The square root of 225, believe it or not, that's a perfect square. So that's simply 15. Plus, the square root of 81 is 9. And then 15 plus 9 is 24. And you're done. Cool, right? That's pretty sweet. Let's do it again. You distribute to drop parentheses. That idea will never change. For our first square root, 2 times 8, 16. X times x, x squared. Minus square root of 2x times square root of 32. 2 times 32, that's 64. Don't forget you still have an x. Okay, be careful with that. Don't just erase an x from existence. That's not very fair. In my first term, I notice I have 2 perfect squares. So I'm going to highlight that. In my second term, I see another perfect square. Awesome. Square root of 16 is 4. Square root of x squared is x. Minus square root of 64 is 8, but we still have a square root of x, and that stays. And you're done. These are not like terms, so you will not be combining them. They do not make a single term. How can they? They're totally different. It's like you telling me that 3x plus 2y is 5xy. I will laugh. I will literally laugh. I'd be like, that's so creative. That is super creative. No, it doesn't work that way. Okay? So think about the fact that they're very different. Okay, maybe I wouldn't laugh. I'd be like, all right, we got to go to the basics. But even still, make sure they are identical. If they're not, you can't combine them. They're not like terms. And that's okay. You just list them one and then the next. No big deal. When we have binomials, recall that you know how to multiply binomials. So let's just do a little recall here. If I had, for instance, x plus 3 times 2x minus 5, you would say no big deal. All I have to do is distribute. I start with my first term and I distribute to everything in the second set of parentheses. Then I move to my next term and I distribute throughout everything in the second set of parentheses, right? And it continues on and on. If you had 3 terms, 4 terms, 5 terms, it doesn't even matter. That concept doesn't change. X times 2x, you would say that's 2x squared. X times negative 5, you'd say that's negative 5x. 3 times 2x, you'd say that's 6x. And then 3 times the negative 5, you'd say that's a negative 15. Of course, you would combine like terms. These are like because they have the same variable to the same power. So you would say, oh, this just becomes 2x squared plus 1x minus 15, and you'd be done with it, right? Same exact idea. Isn't that great? We don't have to worry about reinventing anything. It's all the same stuff. We're just using radicals instead of strictly variables. So, having said that, let's distribute. So I like to draw my lines of distribution. I feel that that's helpful. So we'll start with our 2. 2 times 4 gives us 8. 2 times negative 5 square roots of 6 becomes negative 10 square roots of 6. Remember, you are not multiplying a coefficient by a radicand. It doesn't work that way. You can only multiply radicand by radicand if they're both under the same root. Next, we move to 3 square roots of 6 times 4. 3 square roots of 6 times 4 is simply 12 square roots of 6, and it's positive. And then we have 3 square roots of 6 times negative 5 square roots of 6. So this gives me negative 15. Square root of 6 times 6 is 36. If you all were doing this and you said square root of 6 times square root of 6 is 6, I'm cool with you just replacing this with a 6 as long as you keep in mind you're multiplying that by 5. That's how they're connected. They're connected by multiplication. Don't like create an imaginary plus sign or minus sign. Okay? Don't put one in there that isn't already in existence. So I'm going to highlight my perfect square. Okay? So I have 8. Notice these are like terms. So negative 10 square roots of 6 plus 12 square roots of 6 gives me 2 square roots of 6. Then I have minus 15, and I know the square root of 36 is 6. So I simplify that. They're connected by multiplication. It's not plus. There's no plus sign in between there, so don't write one in there. We have 15 times 6, which is 90. So I have 8 plus 2 square roots of 6 minus 90. And notice I have like terms. So we have 8 minus 90, which is going to give me a negative 82 plus 2 square roots of 6. And there is your final answer. In this box on the side, I ask you whether or not this is correct. So is 6 times 2 square roots of 3 the same as 12 square roots of 18? Hell no. Absolutely not. You multiply your coefficients. You do not take the 6 and then multiply what's underneath the radical. It doesn't work that way, but you already know that. So this is a big no. This is a no, never. 6 times 2 square roots of 3 is simply 12 square roots of 3. You're only going to multiply the coefficients together. Cool. Part B, we've seen before. We have seen this in our very first unit. When we square a binomial, that means we actually have to write it out twice. Must write out twice, right? So we have 5 square roots of 6 minus square roots of 3 times 5 square roots of 6 minus square roots of 3. We have to write it out twice because of that power of 2. If it were a 3, we'd write it out 3 times, right? No big deal. We can multiply that. Once we've rewritten this expression so that it is the product of 2 binomials, then we can distribute. I like to draw my lines of distribution. Like I said, it just kind of keeps me accountable. So I'm going to start with 5 times 5, that's 25. Square root of 6 times square root of 6. Is it okay with you if I say, I know that square root of 6 times square root of 6 is square root of 36, which is 6. So instead of writing square root of 36, I just write 6. I hope you're okay with that. Then let's distribute. 5 square roots of 6 times negative square roots of 3. Well, we have minus 5 times 1 is 5. There's a 1 in front of here. 5 times 1 is 5. Square root of 6 times square root of 3 is square root of 18. Now let's move to the next pair here. So negative 1 times 5 is negative 5. Square root of 3 times square root of 6 is square root of 18. Now let's move to our last pair, and negative times a negative is a positive. Square root of 3 times square root of 3 is square root of 9, which is 3. All right? I just went ahead and I simplified as I went because I want to show you what this looks like if you were to do that. Luckily, you can rewatch the video so you can hear me talk through how I got that. We also have subtitles for the videos if you need to use subtitles instead. Okay? I am going to combine like terms here. So we have negative 10 square roots of 18 plus 3. I'm going to combine like terms again. So we have 153 minus 10 square roots of 18. But I am totally not done. The square root of 18, I can simplify this. I need to look for perfect square factors anytime I have radicals. So I recognize that 9 times 2 gives me 18, where 9 is my perfect square. So this becomes 3 square roots of 2. Replace square root of 18 with 3 square roots of 2. Let's check it out. 153 minus 10 times 3 square roots of 2 leaves me with a final answer of 153 minus 30 square roots of 2. That is how you complete this problem. If you stopped here at 153 minus 10 square roots of 18, you would get the majority of the points, for instance, like on a test or something like that, but it really is not enough. I want you to challenge yourselves to be super analytical, and I want you to challenge yourselves to look at each term and see if you can go further with it, okay? It's kind of like the idea of when we were learning about factoring, that even if you did factor, you should always check to see if you could factor further. And a lot of the times we actually were able to, especially in this class where we had complex polynomials. So we definitely wanted to, and I should say complicated polynomials, where we wanted to factor, and then we said, whoa, I can actually continue factoring because there happen to be levels. So you want to do the same thing here. You just want to be super analytical and go through your answers and make sure, is this in simplified form, right? If you had a fraction, you'd reduce it. If you had a polynomial that said factor, you'd factor completely, not partially. That's weird. You'd factor completely. Same thing with these. Simplify completely. Okay. Let's take a look at the next page. We are doing awesome. Dividing square roots. This section is actually really cool because all this section is telling us is that, hey, you can't have a square root in a denominator. Okay, no big deal. Just like you can't have a 0 in a denominator, here's another rule. You can't have a radical in a denominator. Later on in this section, you'll be informed that you can't have an imaginary number in the denominator. So we want to make sure that when we have, if we ever have fractions as our solution, that we do not have a radical in the denominator. Whenever that happens, we need to use a process called rationalizing to get rid of the radical in the denominator. It's super straightforward. It's really not even a big deal. I think you're going to like this section a lot. Because it's kind of like that idea that we talked about, like square root of 5 times square root of 5 is 5. Square root of p times square root of p is p, right? So we're using that idea again to rationalize these particular problems. So like I said, I think you're going to like this a lot. Check it out. Okay. So for instance, if you had in general form a over b square roots of c, the problem with this fraction is right here. The fact that you have a square root of c in the denominator. In order to fix this, we're going to rationalize. Now, in order to rationalize, this is the cool part, all you have to do is multiply by 1. You're probably looking at me like I'm crazy. Or you're probably looking at this video like, what is she talking about? Our 1 is this fancy expression here. To rationalize, we're going to multiply by whatever that radical is. So in this case, it's square root of c. We'll multiply by square root of c over square root of c, which, by the way, is 1. Check out what happens. If we had a over b squared of c times square root of c over square root of c, first off, a times square root of c is simply a square root of c. And then notice b times 1 is b, and square root of c times square root of c is c. And you've just eliminated the square root from the denominator. That's what you're looking for. Easy peasy. Take a look at example 36, part A. X over 3 square roots of 2. Okay. The issue is the square root of 2. I don't want that there. So I'm going to rationalize by multiplying by square root of 2 over square root of 2. I'm multiplying by 1, so I'm allowed to do this. X times square root of 2 is simply x square roots of 2. Go figure, right? Then we have 3 times 1, which is 3, and square root of 2 times square root of 2, which is 2. But of course, we clean that up. So my answer in this case is x square roots of 2 all over 6. And you're done. That's it. Take a look at part B. For part B, what this problem is trying to do is freak you out. First off, are your eyes drawn to the perfect square like mine? I hope so. I'm going to rewrite this. So first off, square root of x squared is x, but I still have a square root of 5 in the numerator, so I'm going to leave that. In the denominator, I have square root of 3y. This is the problem. Nobody cares that there's a square root in the numerator. Everyone cares that there's a square root in the denominator. So this is the problem. This is what we have to fix. So I'm going to multiply by square roots of 3y over square root of 3y. I'm going to multiply by 1. So check this out. When we multiply, keep in mind, we have x times 1, which is x, square root of 5 times square root of 3y, which is square root of 15y. All over, remember, you're just multiplying the radicands. Square root of 3y times square root of 3y is 3y. Notice that nothing can actually divide out. If it were, for instance, x over like 3x, then yes, I would divide out the x's. But they're not the same, so I can't do anything with this. And guess what? We're done. Always check the radicand, so square root of 15, I know, doesn't simplify any further, which is why I'm really confident about this, and I just leave it as is. If this were a value that can be broken down into a perfect square factor and its other factor, then you need to do that. You need to simplify all the way. But here, notice we rationalized by getting rid of the radical in the denominator. We multiplied by 1. Cool. The issue that ends up occurring is what happens when you have a binomial in a denominator. And it's not just a monomial. Here we had 3 square roots of 2. But what if it were 3 plus square root of 2? Well, that's way different. If it were 3 plus square roots of 2, then this is not going to work. What we have found mathematically is that if we wanted to rationalize, we're going to use something called the conjugate. Okay? So binomial conjugates are binomial expressions that are identical except for the sign between the two terms. So for instance, Here's our binomial, right? The conjugate is the exact same two terms, but instead of a minus, we have plus. So these are conjugates. 2 square root of 3 minus square root of 5, 2 square root of 3 plus square root of 5. Let me show you what happens when we multiply them. So the product of the binomial and its conjugate, let's check it out. 2 square root of 3 minus square root of 5, 2 square root of 3 plus square root of 5. Let's distribute and see what we get. 2 times 2 is 4. Square root of 3 times square root of 3 is 3. 2 square root of 3 times square root of 5 is plus 2 square root of 15. Negative square root of 5 times 2 square root of 3 is negative 2 square root of 15. Negative square root of 5 times positive square root of 5 is negative 5, right? Square root of 5 times square root of 5 is 5. Now, do you see that these are opposites? Positive 2 square root of 15 minus 2 square root of 15, these cancel each other out, which is very cool. So the radical goes away. 4 times 3 is 12, and 12 minus 5, well, that's 7. So the product of a binomial and its conjugate eliminates the radical, and it leaves you with a constant. That is very interesting. Let's see this in action. 5 over 4 plus square root of 3. I have a binomial in my denominator, and that binomial contains a radical. So in order to rationalize, I must use the conjugate. I'm going to multiply by 4 minus square root of 3 over 4 minus square root of 3. Now let's distribute. Keep in mind, if you would like, go ahead and write parentheses around each of your binomials so that it's visually clear what your next step has to be. I find that to be incredibly helpful. We're going to distribute, of course. 5 times 4 is 20. 5 times negative square root of 3 is a negative 5 square root of 3. Remember, here's my coefficient. This is a radical, and that's a radicand. The 3 is the radicand. You can't just multiply 5 times 3. It doesn't work that way. Let's distribute my conjugates. So 4 times 4 is 16. 4 times the negative square root of 3 is a negative 4 square root of 3. Square root of 3 times 4 is positive 4 square root of 3. And square root of 3 times the negative square root of 3 is a negative. Remember, square root of 3 times square root of 3 is 3. I have opposites in this case. Let's cancel those out. And then I'm left with 20 minus 5 square root of 3 all over 16 minus 3, which is 13. This is complete. The only thing I want you to really consider in this case is that sometimes you may want to separate each of these into 2 terms so that you can reduce if possible. So for instance, this is an acceptable answer, or you could write 20 over 13 minus 5 square root of 3 over 13. You see how I split it up into 2 fractions? We've done this a million times. That idea still doesn't go away. I wanted to show that to you because if you could reduce these coefficients, these constants, you really should. Okay? If possible, you really should. Beautiful. Again, at this point, this is a perfect opportunity. Pause that video. Try part B on your own. See how that goes. Make sure you're multiplying by the conjugate and that you're distributing effectively. Don't overthink this. And then just make sure that you are keeping track of all of your signs and, make sure that you're keeping track of all of your products, okay? If you're watching right now, let's take a look together. I'm going to rewrite the problem just so that I can see it a little bit easier. So 4 over the square root of 7 minus the square root of 13. I have two issues, and that is I have two radicals in the denominator. It's a binomial, so I'm going to multiply by the conjugate. Square root of 7 plus square root of 13 over square root of 7 plus square root of 13. Keep in mind, I'm still multiplying by 1. Let's go ahead and put parentheses around these. And that's a clear indication that I'm going to distribute. We'll start with the numerators. 4 times square root of 7 is 4 square roots of 7. 4 times square root of 13 is 4 square roots of 13. That's cool. Now let's distribute the denominator. Square root of 7 times square root of 7 is 7. Square root of 7 times positive square root of 13, that's going to give us positive square root of 91. Negative square root of 13 times square root of 7 is negative square roots of 91. Negative times a positive is a negative. Square root of 13 times square root of 13 is 13. Notice my inner terms, they cancel out, they're opposites. And then I have 7 minus 13, which is going to be negative 6. So I have 4 square roots of 7 plus 4 square roots of 13 all over negative 6. Interesting that the very next example proves to us that we're going to have to split these up into two fractions. So I have 4 square roots of 7 over negative 6 plus 4 square roots of 13 over negative 6. Give me 1 second. Let me fix this. Do you see what I see? I can reduce numerator for denominator. This negative I'm going to move in front. 4 and 6 are both divisible by 2, so this becomes 2 square roots of 7 over 3. A positive divided by a negative is a negative. 4 and 6 reduce again, so it's 2 square roots of 13 over 3. And that is your final answer. That is what you're looking for. Okay, very, very cool. That pretty much covers your operations on radicals. So to just kind of recap, when you add or subtract radicals, they have to be completely like, right? They have to have the same root and the same radicand. They also have to have the same variables if there are any attached to that. It's got to be completely identical. And then you would just combine their coefficients. When we multiply terms with radicals, we multiply the coefficients together and we multiply the radicals together, right? As long as it's the same root. So you, for instance, square root of 5 and cube root of 8, you're not going to multiply those two together, okay? But square root of 5 and square root of 8, yes, that becomes square root of 40, okay? Think about that. With division, essentially what we're doing here is we're focused on the denominator. If there is a square root in the denominator, we want to rationalize, okay? Sometimes it's as simple as multiplying by that, square root or the cube root. If it's a cube root, you got to do it 3 times. But if you have a binomial in the denominator, then you're going to want to use the conjugate in order to cancel out the radicals. So just a few things we really have to keep in mind. I highly recommend index cards. That's going to be hugely helpful. Write down each of these bits of information, like the rules and like an example, so that way you can test yourself and make sure that the concept is really sticking in your mind, okay? We still have some time for today's session, so let's take a look at this next block. Okay. Understand when a radical is simplified. All right, so check this out. A square root expression is simplified when the following are all true. Inside the radical, the exponents are less than the root. Duh, right? We've been doing that this whole time. Constants don't contain any perfect powers for the index. Basically, there are no perfect squares. And then there are no fractions inside the radical. Reason being, if there's a fraction inside the radical, that means there's a square root or a radical in the denominator, which must be fixed. Okay? Which leads us to point 2, denominators must not contain radical expressions. Okay? So for instance, look at part A. Is this radical completely simplified? Can we go further? Absolutely. We saw a whole bunch of these already. Immediately you would say, yeah, the square root of 50 breaks down into 25 and 2 because 25 is the perfect square. And then square root of x to the 7th, well, yeah, that breaks down into x to the 6 times x to the 1st, where x to the 6 is my perfect square. You see how the power is greater than the index? The index is 2. Your root is 2. So because the 7 was higher, we knew for a fact it could be broken down. So then, square root of 25 is 5, square root of x to the 6 is x to the 3rd, and you're still left with square root of 2x. That stays. For the second example, this is not simplified. First off, I see a perfect square here. Square root of 4 is 2, but I still have a square root of 7 in the denominator, which is a huge problem, okay? So I know I'm definitely not done. In this case, what I'm going to want to do is rationalize. So in order to rationalize, I'm going to multiply by 1. It's a fancy one. 2 times square root of 7 is 2 square root of 7, and square root of 7 times square root of 7 is 7. Now I'm done, okay? So that's what we're looking for. We want to make sure that these are completely simplified. And sometimes it just takes a little bit of practice. Take a look at this example. We have 2 square roots of 3 plus 4 over square root of 3 plus square root of 75. This is another perfect opportunity. Pause this video. Give this problem a shot. You can do this. Break them down piece by piece, term by term. If you have to do side work, do it, right? Make sure that everything is nice and neat, organized, so that you don't see a whole bunch of chaos all over the paper. That's not going to be helpful at all. So if you're with me, let's dissect this together. So I'm looking at the first term, 2 square roots of 3, and I'm totally cool with that. I can't simplify it. I'm going to leave it as is. My second term is 4 over square root of 3, so that tells me side work. I have a square root in the denominator, which is an issue, so I'm going to rationalize it by multiplying by 1. This gives me 4 square roots of 3 over 3. Very cool. So we have plus. Now, by the way, 4 square roots of 3 over 3 is the same as 4/3 square root of 3. I just want you to think about that. Keep that in mind. 4 square roots of 3 over 3 is the same as 4/3 square roots of 3. Next, I have plus square root of 75. Let's break that down. Square root of 75 definitely breaks down into 25 times 3, where 25 is my perfect square. Square root of 25 is 5. And here I have 5 square roots of 3. Okay. Now that I have simplified each of my terms, I can now combine like terms. It just so happens they're all like terms. So I have 2 plus 4/3 plus 5. I want to combine all of these. So the easiest ones obviously are 2 and 5 make 7. But then we still have 7 plus 4/3. So again, I'm going to do some side work. 7 plus 4 over 3. We know we need an LCD, so let's fix this. So it becomes 21/3 plus 4/3, which gives me 25/3. So when I combine all of these together, I get 25 over 3 square roots of 3, which I can write as 25 square roots of 3 over 3. Either of these will be perfectly acceptable for this particular problem. If this whole idea still throws you off because you're a little uncomfortable with fractions, which is okay, you can use your calculator to check to make sure you did this right. So 2 plus 4/3, use your ABC key for ABC3, plus 5 gives me 8 1/3, but I want to change that to an improper fraction, so second ABC, and there I have 25/3. So I combine my coefficients, and I have 25 thirds squared to 3, or 25 squared to 3 over 3. So it's a great way to verify that you've got the correct work. Okay, I am pooped. That's enough for today. I think we did a ton of work. Good luck as you watch the videos this week to complete a whole bunch of content pertaining to Unit 3. Keep in mind that your Unit 2 homework is due by Sunday. Some due by Friday, the rest due by Sunday. That includes your bonus comprehension check and your very first test. Once you're all done with the Unit 2 material, which I urge you to finish as soon as possible, then you can move into Unit 3 homework. Please get Unit 2 done so that you can move into Unit 3. We only have 2.5 weeks left of this first session. All right? Good luck, everyone. Thank you for joining me, and please email if you have any questions. I can definitely help you out. Okay? Bye.